So, good evening, everyone. I guess everyone can hear me. So, welcome to the problem solving session week number 6 of this course titled as Semiconductor Devices and Circuits. This is a brief about me. So, my name is Shomnath Bhattacharya ji. I am currently pursuing my PhD at IIT Jodhpur, and I am working towards achieving neuromorphic computing utilizing flexible and organic thin film transistors. And previously I've done my master's and bachelor's in physics. This is the basic class schedule. The last week was a bit different because there was some issue with my network connectivity. but from now on onwards, so like we'll have the class from from 7 to 9 each Sunday. So, so this was the basic course layout. You all are already familiar with it. So, the first week we have learned about basics of quantum mechanics, Schrodinger's equation, how to solve them, and those things. The next one was a basic discussion of the solid state physics, starting of it and those things. Then we have learned about the density of states, Fermi-Dirac statistics, and Fermi functions, and based on this doping, how the Fermi function, Fermi level changes, and that kind of a things. Then we have learned about recombination and generation, different types of recombination and generation, charge transport properties, and those things. And finally, we have known about the continuity equation. And the last week, we have learned about the different kind of junctions, like metal to semiconductor, metal to metal, semiconductor to semiconductor junctions. Now we'll focus specifically on a few key junctions. Those are like P and N junctions. So PN junction. Before that, there was a part remaining of the previous class. So that was we have already learned about the Schottky and the ohmic contacts and those things. So based on that, we haven't learned about the small signal model and low frequency aspect of these devices. So there was a very small part remaining, so we'll learn about that, and after that we'll move towards PN junctions. I won't do what do I say, I won't explain most of the parts through like derivations and everything. You can get that from the from the videos itself, but I'll discuss about the facts and the phenomena happening inside and those things. So let's move to this PN junction class. So these are divided in three parts. So the junctions based on like Schottky and ohmic contacts and those things, then small signal impedance cases, and then we'll move towards the different profiles and characteristics of these PN junctions. So let's start with a brief recap of this week's classes. So the first thing that was remaining was based on the Schottky contacts. So these Schottky contacts based on the low frequency aspects of these contacts. So based on these low frequency aspects of this, so we need to learn about the small signal impedances. So this small signal impedance is majorly of two parts. The first part is the small signal. The small signal means low frequency signals and those things. The small signal resistance. So how do we get this? We get this from the equation of conductance per unit area. So conductance per unit area is dj, that is the conductance. Uh, so this is the conductance per unit area and dj dva. From that we know the value of this. So based on as this is a small signal, so we can assume it as well. J equals to j naught e to the power of qva, that is the applied potential, kt minus 1. So based on this we can do this, and we'll get these values back. So q e to the power of qva by kt divided by kt, obviously, multiplied by j naught. So now we know that j naught e to the power qva kt. So this term is not only different from this, so this is j anyways. So we can write it as like this. So if we inverse the factors, JV as this. So we can get the value of, so the conductance, the reverse of conductance is nothing but the resistance. So from that we can write it as like this, KT by Q multiplied by J, because J naught and this term, This term majorly means of the factor J naught e to the power q va kt minus J naught. So we can write it like this, as in this case J is like this. So from this we can write it like this. So this is the value of small signal resistance, as the signal is very small in that case. Similarly, we can derive the small signal capacitance. So based on this, we can derive the small signal capacitance value. So that is CD per unit area. That will be D of QD by D of VA. So that comes out to be QND epsilon S divided by 2 of built-in potential minus the applied voltage. So based on if it's a reverse or a forward, there will be minus or plus. So that's it. So VA is the applied potential here. So these were already like derived in the videos and everything. So these were the basic thing that was remaining for the Schottky diodes or the Schottky contacts, I would say. And the ohmic contacts are basically nothing but like basic. It will follow the basic Ohm's law, and based on that, we'll only get the value of resistance. So it was omitted in the videos as well. So after that, we have learned about the PN junctions. So what is a PN junction? So there's a semiconductor, and the first half of the semiconductor is doped with p-type impurities, and the next part is n-type impurities. But a p-n junction can be easily made if like two of the different materials of p and n can be can also be joined together, and those kind of a things. So based on that, there are different factors considering that. But let's draw a p-type semiconductor. So if this is a e vacuum, this is ec. So the distance between them are the electron affinity, and we can write it as Is. If this is EV, so the distance between them is Eg, or the band gap. And if there is a p-type impurity present in, so if this is a p-type one, the Fermi level will be something here near the valence band. So this is EFP. Okay. If we are doping the, like if this is the n-type semiconductor or the same semiconducting, the intrinsic semiconductor is same in both the cases, then what will happen is that the vacuum will be at the same level, the conduction band will be at the same level, because this is exactly same, the electron affinity is exactly same. Also the band gap will be at the same level. So this is EV and the distance is EG. But in this case, the Fermi level will be something here. So this is EFN. So this is an N-type. So what will happen if we join these two, these two together? So there would be a band bending happening. Another factor from this, we can say that the work function. So the work function is from. Maybe I'll use a different thing. This is the work function of the p-type portion, and this is the work function of the n-type portion. So we can clearly say that the work function in case of the n-type is much smaller than the p-type one. So based on that, we can assume that the electron flow will be from the n-type to the p-type. Okay. So now, if we draw this, so the first thing we need to consider is that we have to join the Fermi levels. So let's say this is EF. Now, if we can see that the valence band was near to the Fermi level in the first case. So let me first do one thing. So we are assuming that this middle part is the band bending region. So based on that, we can draw it like this. And this was near to that. So it was EV for the P type. Similarly, there was a certain gap between these. So we'll draw it like this. So EV for the N type. There was a certain distance of this. So EC of this. And as the EG of both the cases should be same. So I'm just drawing approximately, but like, so it should be here. Based on this, the vacuum level was here. So it was E vacuum. And based on this, the vacuum level was here. So it is also E vacuum. Now the band bending will happen like this. So this is the basic structure if we join a P type and a N type one. So this is basically called an PN junction. The junction is made out of same intrinsic semiconductor, but one is doped with a P type impurity and one is doped with an N type impurities. So now this in this case we can just let's do one thing. We can extend this part. So this change is known as the built-in potential. So based on the applied reverse bias or a forward bias, or let's say any kind of a bias, this built-in potential will change, and based on that the band bending will change as well. Now this part, the left part, one thing we can say that it receives the electron from the other side, thus the band. So based on this factor, we can say the band bending is towards downward because it's receiving the electron and it's donating the electron. So based on that, the band bending is towards it's upwards. So another factor is that this is the band bending diagram. This is the band bending diagram only at thermal equilibrium itself. So it's only suitable for thermal equilibrium cases. And here's IBI is the, as I will just say, so this is the built-in potential. That is nothing but the potential change due to band bending. As the band bending is happening here, so there's a potential change that is called at the psi bi, and based on that, in case of p-n junction, this region is called as the depleted region or depletion region. So why is it called an depletion region? Because so, clean something. So like if we are just dividing this part into half, so the half in which the n type has the part in it, so there would be so many immobile ions, donor ions there, and in the same case as well. So in this case, there would be so many immobile acceptor ions. So based on this, it is depleted of the charge, moving charge carriers. So based on that, we are saying that it is a depleted region. So this is valid only for the p-n junction cases. So we can say that there are it is majorly consisting of like acceptor ions in the p-type side and donor ions in the n-type side. So this is the basic formation of the band bending structure and the PN junction. And based on that, we can get the different like profiles and characteristics. And if there are any questions about this, you can ask me right now. Otherwise, I'll move to the profiles and characteristics and IV characteristics and those things. If there are any questions, if are there any questions? You can write it in the chat box or like you can write it in the chat box or else you can like unmute yourself and like tell me the query. So if there isn't anything, so we'll move on to the profiles and the characteristics. So another thing in this case that based on the like the derivations and those things, so we have got another unique equation that can be used in so many like math problems and those things. So that is the acceptor concentration dp. So based on this, if you are considering this as the 0 point, so based on this, the distance of this depleted region in in the n type is known as the xdn, and based on this distance it is called the xdp. So depleted region the total depleted region is total x, so that will be xdn plus xdp. And based on that we have this thing. So this is a very unique formula, you have to remember this. And so we'll move on to the next one. So that is different kind of a profiles. So what are these profiles? So first we have to draw this. So I'm just basically drawing this. So if this is let's draw it like this. So if this is the p type and this is the depletion region, this is the mid of the depletion region, this is the n type part of the depletion region, and this is the n type. Now if we are dividing it like this, now so there are few factors we need to know that how they are changing or varying depending on the position of this depletion region and everything. So these factors, like the first one is the charge. So if we are plotting the axis with respect to this, so if we are plotting like this is the distance that is from this is the x-axis, let's say. And based on this, just a second, maybe I'll remove this more cleaner like this. So this axis is nothing but charge. So the variation of charge is basically like this. Just a second. Sorry. So just ignore this tilted line. It will be like a straight line or something like that. So based on this, what will happen that in the P type, there is, as I was saying, in the P type, there is immobile like acceptor ions. So based on that, in the depletion region, there will be net negative charge here, and based on this there will be a net positive charge here. So this is the variation of like charge with respect to this like PN junction, and based on the x-axis, that is the distance we are covering through this PN junction. So the next one, the another key factor we need to understand how it is varying throughout the PN junction is electric field. So if we are plotting like this again, let's plot it like this. So it's another x-axis, and this is the electric field. So based on this change in electric field, there will be a electric field like this. I'll draw the other one here as well, because otherwise I'll have to draw it again. Third one is very simple. That is the potential. So potential profile is another important factor we need to understand. So based on this, it's exactly similar. So the axis is potential on a single side. So this is the potential, and the x-axis is going towards this. So I'm trying to draw this, I guess. Yes, we can draw it. So this is again the displacement or the x-axis here. So based on this area, so that is the starting of the depletion area, there will be an increase in here, and it will increase kind of linearly here, and it will get saturated here. So this thing is nothing but, so this distance is nothing but this like let's say this potential is nothing but the psi vi, that is the built-in potential here. And throughout the depletion region, there's a linear or gradual increase of this potential. Now, so there will be like based on the reverse bias and voltage bias, there will be changes in these potentials. So first understand the application of reverse bias and positive bias, that is the forward bias, and based on that how the band bending is getting like influenced, and based on that how the profiles are getting influenced. So if we are any kind of a bias, let's say under initial bias. So this kind of a bias can be like either positive or negative, and any kind of a thing. So as like uh, I'll just draw it like this. The general band bending was like this. So the if we are plotting this kind of a points, so let's see. This is the depletion region here and here. So based on that, we can say that this was the general kind of a band bending where uh, under no bias. So it is under no bias, okay? And if there's a bias that is already applied to this, so based on the based on the sign of that bias, that let's say the bias is VA, applied potential. So based on that, there will be a change in built-in potential. So the built-in potential will vary like this. So psi nu will be like this, and based on the sign of this VA, so if VA is greater than 0, that is, if we apply a positive bias, what will happen? The VBI, the psi BI will get much lesser. So the thing would look like this. Or we can use the direct line itself. So this will be under influence of positive bias. So now what's happening here is that the depletion region is getting smaller here. So the depletion region is getting shrinked here. Similarly, if we apply, let's say, if we apply VA less than 0, that is a negative bias, what will happen? Psi nu will be greater than this, so VBI plus V, not plus VA actually. So as VA is already negative, so the change will be this as well. But in this case, what will happen is that there would be a change like this. I'll draw it again. Now, based on that, the depletion region will also move. Sorry. And this was under influence of negative bias. So under influence of negative bias, the depletion region will like stretch, and based on that our potential, like the built-in potential is getting increased, and under influence of positive bias the built-in potential is getting decreased, and based on the change in this potential, the depletion region is getting increased or decreased. So based on these factors there will be change in the profiles as well. So if I am plotting this change in files with respect to applied bias, if we are considering that, then I'm just roughly drawing this one. Otherwise, I have to draw this again. So, like, I'm just roughly drawing this. So, if the basic change in charge was like this, sorry, um, if the change in charge was like this, right? So, this was x-axis and this was charge axis. So, under no applied bias, let me redraw that again. So, under no applied bias, it was looking like this, and whichever color. So under negative bias, what will happen that the charge won't increase, but the area will increase. Similarly, based on that factor as well, if it's under a positive bias, this area will decrease. So this will look like this. So the violet one is for like positive bias case, whereas the indigo one, oh sorry, this wasn't it, I guess. The indigo one for negative bias case. So what's happening that the area where we can find the charges are increasing or decreasing. Now based on that, we can also talk about this. We can, I guess, draw it a much bigger scale. So based on this, what will happen that if this is the electric field with this, this was the um, sorry. Yeah. So if this was the depletion region, now in case of negative bias, the depletion region has increased. So it will start from here, but a much higher electric field will be present in this case. Similarly, if we are going to a positive bias, a much lower electric field will be present. But you can see that the midpoint or the mid of this will remain the same. So in case of like positive or negative bias applied, this will be the change on the electric field and based on the same factor as well. Sorry, let me change it again. Yeah, so based on the same thing, if we draw the potential profile, so if this is psi and this is x, based on that, if we are drawing this depletion region, so we can say that this will increase and this will, sorry, this will increase linearly and this will be like this. So this was psi bi. In the first case that there was no bias and everything. So if we are applying a positive bias, what's happening here? If we are applying a positive bias, there's a decrease in this case. So based on that, it will be like this. So this is for the positive bias because the new value of psi bi is minus Va. So this is psi bi minus Va as well as the depletion region is shrinking. So based on that, it will look like this. And similarly, the form will be nearly same as I am not able to draw it like this. So it's looking like this, but so this distance is nothing but psi vi minus Va. But in this case, like Va is less than 0 or under negative bias, that's it. So this will be the addition of these two, that is the psi bi plus Va. So this is the profile changes based on like applied bias, that if we are applying a positive or negative bias. Now, so like there comes like multiple questions. So if the bias is much higher than that, so there will be certain changes. Like if the value of VA is much higher, so there will be a much decrease in the psi bi, and based on that, it will be like here. So it will be here anyways, but like it will be like from here. So based on the value of voltages and everything, it will change. And so, so this was the basic change in profiles, and these were the profiles of charge, potential, and electric field based on the PN junction. So if anyone have any questions, you can ask me right now. Otherwise, we'll move to the IV characteristics.
So why it is important to note down the profile of these?
Yeah, so the profile is required because, like, if we want to know where are the different charges, so let's say, kind of a hypothetical situation, but I am just saying here. So if you know you have a block of this material, right? So let's say it's a metal and it doesn't contain any kind of a charges or something. So if you are going through this, let's say you are scanning the material, and based on that, you can see if, let's say, there's a positive charge here, you will find a positive charge here as well, as it's a conductor, and it will what do I say, like it will propagate the charges throughout the surface and everything. So you will know that there are equal charges here. But based on that, we know in semiconductor, let's say insulator is a different kind of a thing. It will not take any charges, or it will not donate any charges. But in case of like semiconductor, you can say that if you are propagating through it, there can be a positive charge here. Let's say there can be a negative charge here, there can be a negative charge here. So in case of semiconductor, we need to know that what kind of electric field it's creating around itself, and what kind of a potential it is creating around itself. So based on that, we can bias that, and based on that, we can dope that as well. So right now we are at a certain stage where we have only P and N junctions, right? So we right now have a p and n junction. Afterwards, when we get more advanced things and everything, so it will be like a p plus and n junction, where the p side is very highly doped, whereas the n type is normally doped, not like it's anyways highly doped, but not heavily doped. So there's a difference between heavily doped and highly doped. So it can be like this. So for a gradual, so based on this electric field and voltages, so we can also do like this. So it can be like this as well. So what is that? So in this case, there will be like a gradual increase of charges. So in case of p plus type, what will happen? There will be more like negative ions there, and based on that, it will look like this. So there will be a ladder kind of a structure there. So based on this like doping structure and how the material is working, and how we can then change this characteristics based on like our main applicability and suitability. So if we are thinking of using this device as a specific, let's say a conductor itself, just a hypothetical one. Let's say we are going to use it as a conductor. So we generally need that it will just propagate the charge. If I'm finding a positive here, the net amount of positive here, I need to find it there. If we are finding two positive ions here, we need two positive ions here as well. So based on this charge profile, electric field profile, and also the potential profile, we can modify it to our need as well. Is it clear?
Yes, sir.
Okay. So any more questions?
Can we put VA greater than 5 BI in powered bias?
VA greater than 5?
5 DI, the built-in potential.
Oh, okay. 5 psi BI, right? You are talking about that.
Yeah, yeah, yeah.
So you are saying you want to apply VA of 5 BI, 5 psi BI.
No,
I
no,
guess. Okay, okay.
built-in potential.
I got it. I got it. So you are saying that. Sorry. So you are saying that you want to put VA as greater than 5 BI. Let's say 2 BI, like this.
Yeah, 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 something like that. Yeah.
Okay, yes, you can anyways do that. So that will move your material towards like heavily doped what do I say, uh there will be a certain breakdown cases and everything. So based on the value of psi bi and based on the value of va, we have to look at it. So
Okay.
so you are saying
Oh,
there will be a like a positive or negative change, so there will be a sign change as well. Okay.
yeah, mostly the depletion formula and all. I was just wondering that.
Yes. Okay, okay. Just let me think about it. Just let me have a moment. So if we are using that, yes, we can certainly apply that. Yeah, we can certainly apply that. So because psi bi is anyways not that much high, and we are applying va of much higher in the physical cases, I am saying we apply much higher cases, then in that case there will be a certain change in the band bending itself. For the calculation purposes and everything, we tend to use this, but it can be of any limit itself. So va is greater than 0. There can be breakdown in the material itself, but that will be a
Okay,
different case. We can apply that.
okay.
Any other questions? If not, then like in the videos itself, there was derivation of the forward bias cases, that how the current and voltage characteristic will happen and those things. So I am talking about the IV or the current voltage characteristics. So if we make a diode out of it, so a p-n junction diode, the basic thing sorry, basic characteristic everybody know is this. So this is voltage, and this will certainly be negative voltage. This is current, and this is negative current. So the direction is changed in both the cases. So in case of voltage, the direction is changed, and for the current, the direction is changed. So in this case, if we are applying a forward bias, so there will be a certain increase of this in a linear region, and at a certain point, at a certain point, it will start increasing exponentially. So this point is called the knee point, and at a certain voltage it starts working like rapidly, so this is called as the knee voltage, and the point is called the knee point. And this particular case is for only forward bias. Similarly, in case of a reverse bias, there will be a very minimal current here, like this, and it will keep on increasing but at a very slower rate than the knee case. So like here we are like the plot shows like the at the knee voltage the current is uh, let's say, sorry, yeah, so the current looks like this, right, only this much. And in case of this the current look like similar, but the reverse current or the reverse bias, at the reverse bias condition the current is very much smaller than the knee current itself. So for the drawing purpose I am drawing like this, but this value is much higher than that. And now what will happen is that after you give a certain amount of voltage, certain amount of negative bias, that is the negative voltage, there will be a instant breakdown of the devices. So this point is called as the breakdown point, and the voltage that is required to apply is called the breakdown voltage, and this phenomenon is called the breakdown. So this is essentially a bad phenomena of your devices because your device won't be able to take much higher voltage than this. But based on this, we have several like unique diodes as well. That is called the Zener diode and those things. But most of the devices work on the forward bias region, and this is the reverse bias region. So based on different kind of junctions and different things, so we have several important diodes. You can learn about that separately. So those are the Zener diode that works specifically on the breakdown region. There is something called the pin diode, PIN diode, and based on this factor, there are several photodiodes as well. So without applying any kind of a voltage or something, we are just shining light on top of it, and based on that, so like the photo detector is basically that. So if you are shining light on top of it, it will, what will it do? It will excite the both the sides, and based on that, there will be current flow between these two junctions, and that is called the photodiode. So based on different phenomena, we can get like based on different materials as well. So several materials is able to achieve this electron hole pair generation through photon through like applying photon on top of them. So those kind of materials can be used to make this photodiodes, and several materials that is like not able to achieve these kind of phenomena that will be used in different case. So in case of like pin diode, there is that a p-type portion, there will be an intrinsic portion, that is the I portion, that is the intrinsic one, and after that there is a n-type. So there are several advantages of using this kind of a thing. It will remove the depletion region and those things. So there are several kind of a diodes, so you guys can like learn about those and as well. So I guess this was like this week's work. So like we'll move to the problems and everything. So I'll share the first one. So this week we'll only look into the like numerical problems. Just a second, let me write it down. Just a, so an
So
average.
one small doubt.
Hi, yes, sure.
So why these semiconductors are only applicable for the electric field instead of magnetic field?
Okay, so like based on the factor that like we are applying a voltage and everything because of this electric field itself. So like we are only considering the phenomena of an electron and a hole. So based on this electron, if there is nothing there, or the electron is leaving an leaving an what do I say leaving the valence band, we are saying that there's a charge that is hole. So based on the applied electric field, this electron and hole reacts, and there is no current like phenomena that based on that magnetic field this electron and hole changes their path or changes their mobility. So that's why we are concerned more about this like electric field and those things, because we are considering there are like several electrons and several holes, and this is the basic understanding of that, nothing else.
Okay,
Because
sir.
so if we are applying a voltage, that will increase the that will increase the electric field, and under influence of that electric field there will be more movement of the electrons and the opposite movement of the holes and those things. Yeah, so I'll write it down. So an abrupt silicon PN junction. And also one important thing is that we are considering PN junctions that are like in physical cases, the PN junctions, so the P part and N part can be out of even like different materials as well. But in all of the cases we have until read, or like we are solving problems for our like for a single kind of a semiconductor. So right now even in this question as well, so we are saying that silicon PN junction. So a silicon PN junction is nothing but a silicon that is p type and a silicon that is n type, that are connected together, or you can say a silicon that is doped different types in both of its parts. So where was I? So yes, an abrupt silicon PN junction is at temperature of 300 Kelvin, is uniformly doped with Na of 10 to the power 18 cc and Nd of 10 to the power 15 per cc. The area of the junction is 6 into 10 to the power minus 4 centimeter square, and inductance of 2.2 millihenry is placed in parallel with the junction. Calculate the resonant frequency if a reverse bias of 1 volt is applied. And there are few given parameters as well. So kT by Q is nothing but 26 millivolts. As it is temperature, the temperature is already shown as 300 Kelvin. Value of Ni is 1.5 into 10 to the power 10, and relative permittivity of silicon is 11.7. So try to solve this. And also another factor that I would like to show you that in most of the problems, the value of Ni is either 10 to the power 10 or 1.5 into 10 to the power 10. So based on that, in different problems as well, there won't be a written number that what is the value of Ni and those things. So in those cases, you will have to consider 10 to the power 10. And if there is a given number, you have to follow that. So try to solve this. Let's take 2-3 minutes and then I'll discuss the problem as well. So anyone was able to solve this? So I'll give a simple hint, I guess. So first try to calculate the built-in potential. From that you can get the value of depletion width, and based on that depletion width it is very easy to calculate the resonant frequency, because then you will have all the parameters to get the value of resonant frequency. So the value is 1 by 2 pi root LC, so like that. Try to do this. Then I'll solve this. So first we need to know understand what is the value of psi bi, that is the built-in potential. So the value of built-in potential is nothing but kT by q ln of NAND by Ni square. So from that we can write it as like this, as it is already given 26 MV. Otherwise, even there was no written value of this, it would be anyway 0.026 because it's a constant. And then ln of, so what is the value of Na here? So Na was given as this 10 to the power 18, and Nd is 10 to the power 15. So 10 to the power 15, and in general it's this, but in this case it will be 1.5 whole square. So let's put on the values, just a second. So the values are 0.026 multiplied by 29.122. That is nothing but 0.7571. So the value of built-in potential is this in volts. Now we need to understand what is the value of W. So W is the depletion width. Now the value of depletion width comes from this 2 epsilon s psi bi minus the applied voltage multiplied by Na plus Nd whole divided by Q multiplied by NaNd. So from this we have to just put the values. So 2 into epsilon s. So epsilon s is nothing but 11.7 into, because the relative permittivity into the free space permittivity. So that is this into 8.854 into 10 to the power minus 14 multiplied with, okay, so now the case is here that Na plus Nd Na is 10 to the power 18 and Nd is 10 to the power 15. So anyways, it will be 10 to the power 18. That is the value of Na would be, as its Na is much higher than Nd. So it is nothing, it is nothing but 10 to the power 18 multiplied by psi bi, that is the value of psi bi we have found out as 0.7571, and the value of Va is how much is the value of Va? Value of VA oh, sorry. So the value of Va is 1 volt, so it will be 1.7571 divided by this, the value of Q, multiplied by 10 to the power 18 and 10 to the power 15. So let's put it down as like this. Seven into 8.854 into 1.7571 whole divided by 1.6. So if we are writing it like this, let's write it as, so 364.04 something. So we are omitting the points after that. So 364 multiplied by 10 to the power 4 divided by 1.6 multiplied by 10 to the power of 14. So this would be 227.526 into 10 to the power of minus 10. So it would be as 0.000158, and it will be in meters. So if we write it as like micrometers, so it would be sorry, not this, sorry. So if we write it as like micrometer, so we can write it as like 151 or even like 150.8. So from this we have to calculate the value of, sorry, so we have to calculate the capacitance value. So that is nothing but the value of Cj. So Cj is C epsilon S A divided by W, the depletion width. So the value of epsilon S we know, that is 11.7 into 8.854 into 10 to the power minus 14. The area was given already in the question, so it is 6 into 10 to the power minus 4. So this is nothing but 6 into 10 to the power minus 4 whole divided by, we have got the value of W, that is 1. Okay, anyways, so we can write it as like 150 into 10 to the power, no, sorry, 1 150.8 into 10 to the power minus 6. Now if we put all the values, let me just put them, 11.78.854 into 6 divided by 150.8. So the value is 4.14 multiplied by 10 to the power 14, 4. So that is 18. 18 minus 6, that is 10 to the power minus 12. And this is in farads. So normally it comes out in the range of nanofarads, but in this case it's coming as 10 to the minus 12. So that is femtofarads. Anyways, so we have to calculate the resonant frequency. Resonant frequency. So we know if naught is nothing but 1 by 2 pi root over L and C. So the value of L was given as 2.2 millihertz. So if we are putting the values of this, 2 pi into root over of, so 2.2 milli, so that will be 2.2 into 10 to the power minus 3 and 4.14 into 10 to the power of minus 12. I guess there is some kind of a miscalculation. Anyways, you guys can like recheck the calculations and everything, because it shouldn't be like this much. 4.1, sorry, 4.1 into 2.2, that is 9.1108 root over of 9.108 into 10 to the power minus of 15. The value is 1667664.257 in Henry. So, sorry, not in Hindi, it will be in hertz. My mistake. So it will be in hertz. So let's write it as 1.667 megahertz. So the resonant frequency will be 1.667 megahertz, or you can write it as like this 1.7 megahertz. So this is the value of resonant frequency. So if anyone have any question, you can ask me, or we will move on to the next question. So these are the basic formulas what we have already used. So the value of depletion width, we can directly like get it from here. And so this is, oh, sorry, this is nothing but the value of Na itself. Okay, and the value of psi bi, will use it in most of the problems in this case. And these are the value of resonant frequencies directly from the like the impedance and everything calculation. And the value of capacitance is epsilon s A by W. So we'll move on to the next one. Question number, just a second. Let me write it down first. So the question is, the current through an ideal PN diode at 300 Kelvin is 2 milliampere when a zero point 0.1 volt forward bias is applied. Find the reverse saturation current. So they are saying that it is an ideal PN junction diode where at room temperature the current is 2 milliampere when a zero point 0.1 forward bias is applied, and based on that we have to find the reverse saturation current. So as I have not discussed it in the class, so I'll write it down. The formula is this, nothing but, sorry, VP minus 1. So this is the basic formula here. Just put the values and you will get the values. So if a VA is the applied bias, and VT is anyways, you will get it from here. Are there anything I have to say? So IS is the saturation current, the reverse saturation current, or the current when there is no voltage kind of applied, or leakage kind of those kind of things you can say. So from this you can get the value of IS. So we need to find the value of IS here. Just put the values and get the answer. It will take a minute or so. So anyone was able to get the answers? So if we are just changing this equation, it will look like this. I divided by e to the power of VA by VT minus 1. If anyone has not got this, so the value of I is already there, so that is 2 milliamperes divided by e to the power of the applied forward bias was this 0 0.1 divided by kT by Q, that will be the value of 0.026 minus 1, or the value would be 2 into 10 to the power minus 3, that will be. So the value is into 0.0218, or the value will be 43.656 microamperes. So this is the value of this. We'll move to the next problem. Question number 3. So we have a charge profile of a PN junction such that it is N type for minus W to X to minus zero point 0.5. It is intrinsic for minus zero point 0.5 to X to zero point 0.5, and it is P type for 0.5 to X to N. Now all the units are in microns. We have to find psi bi, that is the built-in potential, and the given values are Na equals to Nd equals to 10 to the power of 15 per cc. They have given the value of Kt by Q as 26 millivolts, and the value of Ni is given as 10 to the power 10 per cc. Let's find it out. Take 1 or 2 minutes. The formula is exactly same what we have used for psi vi and everything. I'll give the formula then. So at first we know Q psi bi is nothing but the difference between the C type EC and on the N type of EC, and we also know that the value of ND is nothing but NC exponential of EF minus EC of N divided by KT, and of the acceptor side, or we can write it as like for this side it will be Ni squared by Na, right? That is NC exponential of EC EF minus ECP E of N minus, sorry, KT, right? From there, if we are dividing both, we can get the value of this NDNA by Ni square equals to exponential of ECP minus ECN divided by KT. From that, we can get the value of ECP minus ECN equals to nothing but KT ln of NA by Ni square. From that, we can write that the first value is nothing but Q pi KT ln of NA by Ni square. So the formula we have been using until now is Q psi b KT by Q. So this is a constant value anyways. Ln of NA by Ni square. Now, if we are putting the value, so that will be 0.026 ln of 10 to the power 15 into 10 to the power 15, as both the values were same, by 10 to the power 20. So I guess it was not given. Yes, so it was given as 10 to the power 10. So we are putting it like this. So the value will be, just a second, the value will be 0.5986 volts, or zero point 0.6. You can write it as like this can be written as this or any of this. So like this is the basic formula that we have been using until now, and in most of the problems you will be using this, and based on this like derivation and everything. So if you have two types of p, two types of n, and those kind of things, in those cases as well the same formula can be used. So let's move on to the next question. So we have a junction like this. Okay, so this is nothing but ND, this is the X. Now we have on the right side the value is 10 to the power 15. On the left side we have the value is 10 to the power of 16. So both are in CC obviously, so let's write it down like this. Now we have to find the value of psi bi for the given profile. So as I was already saying that in case of both P, P and both N and similar kind of like a similar kind of a doped structure. So if we have, let's say, this can't be like already called as the, let's say, um, no, we can't call it as like P plus P or N plus N like that. It because they are both nearly at the similar doping levels, but it is kind of a P, P and N structure. So same kind of a doping is happening on both the sides. And I guess I'll just sorry. So I'll just delete this part because otherwise it will create confusion. Okay. So let's try to find it out. Now the same formula will be applied here, right? Psi bi q psi bi is nothing but EC2 minus EC1. So we are just considering a 2 and 1, nothing but that. And in this case as well, ND1 we can say is NC exponential of EF minus EC1 by KT. Similarly, we can write it down as ND2 NC exponential of EF minus EC2 by KT. So these are the basic equations, and from that we can derive the value of built-in potential, and we have to just put the values there. as we know that for the first case the value is 10 to the power 16, and the second case the value is 10 to the power 15. Just take 2-3 minutes and try to solve it. I'll just solve the problem, I guess, and then based on that, you can just put the values. So just we are dividing both of the cases. So if we divide both of the cases, NC and C will get cancelled out, and based on that, we can write it as EC2 minus EC1 divided by K. Ah, no, sorry. KT will also get. Oh, no, no, sorry. KT will be there, and from that we can write it as like this, psi bi, because this difference is q psi bi, so it will be nothing but kt by q ln of nd1 by nd2. So similar to the previous case when we have got the value of na nd divided by ni squared, in this case we are just getting the ratio of both the cases. So based on that, if we are putting the value 0.026 ln of the first one was 10 to the power 16 divided by 10 to the power 15, so that is 0.026 ln of 10, and the values will be 0.05986 or 59.86 millivolts, or we can also write it as 60 millivolts. So okay, so in this case it was 0.6 volts, whereas in this case it has like we have got the value of 0.60 millivolts, not 0. So we'll move to the next one. Now question number, uh, this one is 5, right? Yes. Question number 5. We have an ideal PN junction diode in forward bias such that the applied bias is much greater than the thermal voltage. How much voltage will be required to increase the diode current by a 10 times factor. So from the question, we can say that an ideal PN junction diode is forward biased such that the applied bias is much greater than that. So from that, we can get this. So the thermal voltage is much greater. Sorry, the applied voltage is much greater than VT. So we know the formula is nothing but this, right? E to the power of VA VT. So this was the basic formula. But in this case, what has happened that uh, or else we can write it like this maybe, no? So here from so it was nothing but this, right? Minus 1. Now let's write it down first like this. So right now VA is much greater than VT. So VA is much greater than VT. So then e to the power of very high number. So we can just remove the value of this, nothing but this. So based on this, we can write it like this. So what has been said that it is much greater than the thermal voltage. Now, how much voltage will be required to increase the diode current by 10 times? So from this we can write it like this. So if the problem says this much voltage will be required, let's say, so the applied voltage is del VA. So if we are using this, what will be the new current? The new current will be 10 times of I. So based on that, we can just rewrite the equation like this. I naught e to the power of VA plus del VA divided by VT. So from that, we can write it as like this, right? E VA by VT e to the power of del VA by VT. Now this the first factor is nothing but the value of I. So this is del VA by VT. So I cancel out, and based on that, or let's write it on the next page. Let's rewrite it. I multiplied by e to the power of till change in VA by VT, or from that we can write it as like till VA is, sorry, I cancel out. So it is nothing but till VA is how much? Have they given the value of VT here? I don't think so. So the value is nothing but this VT multiplied ln of 10. So the VT value is 0.026, right? So we know this value anyways, and ln of 10. I guess from a last problem as well, we have got this, right? Yes, so that was 59.86 millivolts. So the value is nothing but 59.86 millivolts. Or you can write it as like 60 millivolts. Okay. So we'll move on to the question number 6. Question number 6. Okay. Now consider the given circuit. I'll draw the circuit below, but so in a forward bias condition, DC current I is 13 microamperes. Okay. Now the thermal voltage at room temperature is 26 millivolts. So we know that already, right? And from that we know that junction capacitance of this PN junction at operating point is just 1 nanofarad. So we know the junction capacitance from this. They have also given us the angular frequency, that is the value of omega, that is 10 to the power of 6 rad per second. So we have to find the small signal current. So we have to find the value of small signal current as we have already discussed, right? Okay, so first we need to know the circuit itself. The circuit looks like this. So the diode is here. We have a 100 ohm resistance. We have a source here that gives us 5 sine omega t millivolts. We have a voltage source here as well, and this is grounded. So we know the DC current that is 13 microamperes. So let's try to solve this. Take about 4 5 minutes to solve this. So I'll solve this now. So first we need to know what is the AC resistance of this diode is. Okay, that is the value of RD. So that is nothing but the thermal voltage divided by the current through it. So the thermal voltage as already given is 26 millivolts. Sorry, 26 millivolts divided by 13 microamperes. So that is nothing but 2 and milli and micro. So that will be in kilo ohms. So we know that the AC resistance of the diode is 2 kilo ohms. Now, if we just draw the diagram for this, this would look like this. So we have a capacitance here, we have a resistance here, we have the resistance here as well, and we have the source here. Is the equivalent circuit. Okay. And this is also grounded here as well. So right now we know the resistance of this, that is 2 kilo ohms, and let's assume this as uh, this. Okay, let's assume it as this, and this was already given as 100 ohms. Now what we'll have to do is that we know that the AC current is nothing but VAC by Z1 plus Z2. Okay, so both will be under mod. So right now we have to find the value of Z1. So the value of Z1 is nothing but this, right? Both are in parallel connection. We know the value of RD here already. So from that we can write as so this will I guess no, sorry, sorry. First we let's calculate the value of minus jxc, and then we'll go towards other things. So as we know the angular the angular frequency here. So first let's try to calculate the value of xc, that is 1 by wc, right? So the it will be 10 to the power 6 into 10 to the power minus 9. Okay, as it's 1 nanofarad, and the frequency 10 to the power 6, so this will be 10 to the power 3. So based on that we can have the value is minus j omega c, so the value will be minus j or minus 10 to the power 3 j, right? So the value will be like this. Now we know the value of z1, so z1 we have to calculate it directly through that. So that is minus jc parallel with the value of rd, that is 2 kilo ohms, so that is 2 to into 10 to the power 3. So based on that we can write it like this, right? Or multiplied by rd divided by sorry, plus this and minus jc into rd. Just let me think for a bit. 1 by c plus 1 by rd divided by, yes, so this one will be that. um or I am mistaking it. No, sorry. This one will be the multiplication term and this one will be the plus term. Okay. Now we'll just put the values here. So this is nothing but 10 to the power 3j multiplied by RD is 2 into 10 to the power 3. So that will be okay. We'll calculate this afterwards. So this value is nothing but 2 into 10 to the power of 3 minus j into 10 to the power of 3. So we'll just remove the 10 to the power 3 term, so it will be nothing but minus of 2j divided by 2 minus j into 10 to the power 3. So the term will be like this. So the impedance value is this, right? Minus 2. Yes, up until now it's okay, right? Now we have the value of j2 anyways, so we'll just get the value of j1 plus j2. So j1, what is j1 plus j2? j1 plus j2 is nothing but minus 2 into 10 to the power 3 into j divided by 2 minus j, and the value of j2 was how much? 100 ohms, right? So this is okay. So this one is in ohms. So the value will be nothing but 100 ohms, 100 ohms. So the value will be 100 ohms or no, so sorry. So this one will be 0.1. So based on this, we'll just get the values here. So this is 2j into 10 to the power of 3 plus 0.2, right? So this is 0.2, 100 ohms, 100 ohms. I guess no, this one will be like this. So this will be 10 to the power of 3, okay? And minus of 0.1j into 10 to the power of minus 3, okay? So this one will look like this. So if we are just dividing the factors, let's remove the 10 to the power 3 factor outside. So it will be 0.2 minus of 2.1 j by 2 minus j. Okay. So we have got the value and we'll just mod the values. So we'll just have to. So we'll get the 10 to the power 3 anyway. So that will be root over j1 square plus j2 square. We'll get the value anyways. So we'll just mod it. So this will be 0.2 whole square plus 2.1 whole square divided by 2 square plus 1 square. Okay, based on this, this will be root over 0.04 and this is 441 divided by root over of 5. Let me put the values here. Oh, sorry. So it will look like 0.04 plus 4.41, that is 4.45. Root over the value is 10 to the power 3 of 2.1095, or we can write it as like this. And root 5 is 2.236, something like this. So we'll get it like, let's uh, let's put the whole values, I guess. 2.236. So the value is nothing but 0.943 multiplied by 10 to the power 3. It will be in ohm. So if we are going towards kilo ohm, oh no, so let's wait. So we'll have to also divide the values. So the final value will be J of AC is nothing but V of AC divided by J1 plus J2, right? So V of AC was how much? 5 sine omega t, right? So it will be in millivolts, right? So the value is nothing but this, divided 0.943 into 10 to the power 3. Okay, so this is good. This will cancel out. So the value will be 5 divided by 0.943. So based on the approximation, it is looking like this in M. Oh, wait. So the value is, uh, I'm sorry, just remove this. So this is 10 to the power minus 3, but this one is 10 to the power 3. So we can't cancel it out. So into 10 to the power minus 6 ampere, or let's say write it as like this in 5.3 microamperes. Okay. So we'll have another problem solving session, problem, as we still have got time for the rest. So I'm sorry. Yeah. So let's consider an ideal PN junction which is operating at T equals to 300 Kelvin in the room temperature itself, with doping densities of accepted doping is 10 to the power 17 and donor doping is 10 to the power 15 per cc. Both are per cc actually. Okay. So now assume intrinsic, I don't know if it's coming up on screen. Okay. Now the intrinsic carrier concentration, that is Ni, is 10 to the power 10. As I have already told that the values are either 10 to the power 10 or it is considered as 1.5 into 10 to the power 10. So that's it. And now we have to calculate the built-in potential in the junction. So we have in this session as well, we have multiple times used this. So take a minute or two to just solve this.
So 0.7184.
Just a second. Let me just put the values. Just a second, right? 0.026 ln of divided by 10 to the power of 17 into 10 to the power of 10 to the power of 15 into 10 to the power of, what was it, 10 to the power 10, right? So that will be minus 20. So this is this, and we should get the ln of this. So what was your answer?
0.7184.
Yeah, it's correct actually. So just we have used the same formula over and over again. So psi vi is nothing but kt by q. We know the value as well, 0.026. We need ln of 10 to the power 17, 10 to the power 15, and divided by 10 to the power 20. So we'll get 0.026 ln of 10 to the power of 12. And from that, what do we have? Just a second. 0.026 multiplied by 27.631, and from that we get the value of 0.7184 volts. That's the correct answer. So with this, we'll conclude this session. And if anyone have any question, please ask me about these problems and those things.
Hi, Somnath. Can you hear me?
Yes, yes, sure.
Yeah. So I have a question, actually request. It's related to something else.
Yeah.
So could you please provide the solution of previous assignments?
Previous
Because
assignments, like,
the assignments we are solving in the after every session.
oh, okay, okay. So, like, based on the previous week's assignment, you were saying, right?
Yeah, yeah, yes, yes.
Yeah, sure. Then, if okay, so I may take extra class after this regular 12 classes. So I'll then like discuss those assignments on that class, because otherwise it will based on the schedules itself. So like as I am going through the problems a bit, and then we are just discussing the few of the problems, not much. So is it okay to then I'll discuss those problems on so there are, I guess there are like few similarities between the problems as well, right? which I am just discussing, and the problems given on the
Yeah, they
assignments.
few of them are same, but what?
There are a few others as well. Okay, okay,
Yeah,
I
yeah.
got it. So like then what I'll do is that because like it will take like a certain amount of time in from each of the classes, and we are already at the halfway point of the
No,
course. So
is it possible just you solve and share it with us? That is also problem. You don't
no,
need to.
what I was thinking that then like I'll take like with just removing these 12 classes, I'll take an extra class in which we'll discuss the like the issues throughout the course and those things. So what I'll do is that then I'll just divide that class into two parts. The first part I'll then like discuss the problems and the assignment solutions and those things, and the other half, that the other 1 hour will discuss the issues throughout the course, lectures and those things. I guess that will be okay, right?
Yeah, no problem.
Yeah, sure. So like I'll do that. Then we'll discuss the assignments, and then we will have some question answer sessions and those things. And even if like there is much lesser time, then I'll provide the full solution through that day as well. Okay.
Thank you.
Sure.
Thanks.
Thank you for attending the session. So we'll conclude today's session. So thank you.